Had some questions about this problem, 20.52, so I thought we'd go over it. So we're trying to find the electric field at some point x from a dipole. So at some point, and here we're on the x-axis. So we're on the x-axis, some point x from the origin on a dipole. So in class we did this, we tried to find the dipole on the y-axis, now we're trying to find it on the x-axis. And so the first thing we like to do is, let's go ahead and label our charges. So I'll call this charge 1, and this is charge 2. And let's look at our electric field on this axis. So the electric field from charge 1 will point this way, it points away from positive charges, and it should point this way towards the negative charge E2. And I'm trying to be a little accurate here. The E1 should be bigger than E2 because the positive charge is closer. So we know that our force or our electric field is going to be strictly in the x direction. And so our equation will look something kind of like this. KQ1 over R1 squared plus KQ2 over R2 squared. And so now we've got to go through. So let's just call the charge in each case Q. And so now what is our R in this case here? Well, the R is going to be the distance from the charge Q, or charge 1, and the point in question. So it's R. And if you look at our picture here, X is the distance here, and then A is this distance. So this should be X minus A. So you want to stop here and make sure that that makes sense to you. Now for the second one, because it's a negative charge, I'm just going to pull the negative out front. And so this distance here is going to be different. The R1 would be, I'll draw it over here so it's a little bit, and so this is going to be R2, and this is going to be X plus this little extra distance of A. So X plus A. All right, and so this would again be the electric field in the x direction. And this is really all you need to start out. So if this is on a test, you could just sort of stop here and say, this is the electric field in the x direction. So this is the electric field. Now what the book wanted you to do is it wanted you to show you that when x is much, much bigger than A, okay, this formula we just derived turns out to be the same as equation 206b from the textbook. And so that's what we like to do now. And so in class, if you remember, what we did with this is we said, okay, well, if x is much, much bigger than A, we can neglect the A. And if that happens, over here, okay, it approximately comes KQ over x squared minus KQ over x squared equals 0. All right, and so this is the problem. You can't just do this approximation. And what this is kind of getting at is the idea of a Taylor series approximation, which you've done, probably done in calculus. And so if you want to do that, you can, although there's other ways to sort of look at this. And what this is saying is to the first order, when you're really, really far away, because it's one positive and one negative, then it basically looks like no charge at all. Now we want to be a little bit more careful and look at the next order from that. Okay, so this way doesn't work, and so we got to look and try to find another way to approach this. So all I'm going to do here is I'm going to add these two together by finding a common denominator. And so for this guy here, to get the common denominator, I would do x minus a squared, and then I've got to multiply the top and the bottom by x plus a squared. And then for the other one, I already got the x plus a squared. So I multiply it by x minus a squared. And then when I add those together, what I've got then is something kind of like this. So I can pull out the KQ. And so in there I'll have x plus a squared minus x minus a squared, and then all of that is going to be over x minus a squared, x plus a squared. So I just added together these two fractions and then pulled out the k over q. And if you look at this, if I expand this out, okay, I get, just from doing, expanding, if I actually write out the x plus a times x plus a, I get x squared plus 2ax plus a squared, and then I get minus x minus a squared, which is x squared minus 2ax plus a squared. So again, and that's all over the common denominator guy we had, x minus a squared, x plus a squared. And so now you see that when I do this, when I apply the negative sign, the two x squared pieces will cancel and the two a squared pieces will cancel, but it'll be 2ax and then minus minus 2ax, so those will actually add up. All right, and so what I'll get then is 4ax. We still have that kq piece outside, and then all over x minus a squared, x plus a squared. So that's our exact equation. So that's the exact same equation as this. We just sort of made it a little easier to look at by doing a little bit of algebra. But now we see that what I can do is, for the case where x is much, much bigger than a, all right, so these downstairs pieces I can write as x squared and x squared. So on the bottom I get to the x to the 4th power, and on top I still have the same pieces, kq 4ax, and one of those factors of x will cancel. And so I get kq 4a over x cubed. All right, and then just realize that in the book it uses this idea of the dipole moment, which is the distance between the charges times the charge. So for us, the dipole moment is 2a, the distance between them, times q. And so you can write that in terms of p and get the same equation from the book. We're not going to focus on that, so I wouldn't worry too much about that p, but just if you want to make sure it does agree with the book. And then just real quick, I'll just make sure this is really clear that this is actually a 3 down here.